In this video, we're going to solve a practice problem related to the theorems for existence and uniqueness of solutions to differential equations. So we have two ODEs here we want to try to solve. We have the first one, ty prime plus 4y equals t squared plus 1 over t. And the second one, y prime is 2ty squared. First, we want to classify in terms of linearity. So based on the form of the structure here, this first equation here is linear. The y's are only on the left-hand side in the right nice form. The first here is linear, and the second, because of the y squared term, is nonlinear. Now the problem says for the first, to find the general solution and determine the interval of existence for different solutions for y of 1 equals a and y of negative 1 equals a. So we have our equation we want to solve here. This is our standard first-order linear equation, so we're going to put it first into standard form by dividing through by a t, and then find our integrating factor here, which will be e to the 4 log of t, which ends up being t to the 4th, giving us a modified equation of this form. This left-hand side is a productable derivative. It is t to the 4th y all derivative that we can then integrate both sides of the equation. If we do that, we will get t to the 4th y on the left. On the right, we will get t to the 6th over 6th plus t cubed over 3 plus c. And dividing through by t to the 4th gives us our solution worked out of y of t is t squared over 6 plus 1 over 3t plus c over t to the 4th. So that is our general solution. And if I want to look at y of 1 equals a, well, it's going to give me that a should equal 1/6 plus 1/3 plus c. 1/6 plus 1/3 is a half, and so c is a minus a half. And my solution here is going to be y of t is t squared over 6 plus 1 over 3t plus a minus a half over t to the 4th. And for the second condition, which was y of negative 1 equals a, we end up with a equaling 1/6 minus 1/3 plus c. 1/6 minus 1 is negative 1/6, so c is a plus 1/6, giving us y of t squared over 6 plus 1 over 3t plus a plus a sixth over t to the 4th. Now in both of these, we notice that the only issue with the solution are the t's in the denominator. There are no other things about this that can force it to not exist. And therefore, for all of these, the only issue is that t equals 0. The solution that is started at 1 with y of 1 equals a, this will exist on the interval from 0 to infinity because it has to include 1. And similarly, the one with y of negative 1 equals a also can't cross 0, so this will exist on minus infinity up to 0 because 0 is the only issue here. It's those t's in the denominator. Tying this back to our theorem, we look back at our equation in standard form, which is right up here. The only issue here are the discontinuities at t equals 0. We have the 4 over t, and we have the 1 over t squared. Both those give us discontinuities, and so both of those give reasons for why the intervals should stop at t equals 0. That's what we see here in this case. We end up having a scenario where the solutions both stop existing at t equals 0, and so we can't guarantee anything past that point, which works out for this case here. And that works by applying the linear theorem from this section. Now we have our second example with the nonlinear theorem. Our second example was y prime equals 2ty squared. This is separable, so we know how to solve it. Y prime over y squared equals 2t. So 1 over y squared dy equals 2t dt. Integrate both sides. Negative 1 over y equals t squared plus c. So y equals negative 1 over t squared plus c. If we start with y of 0 equals a as a question about the problem statement, we can then solve for c. This should be negative 1 over 0 plus c. So c is negative 1 over a, meaning our actual solution here, y of t, is going to be negative 1 over t squared minus 1 over a, unless a is 0. If a is 0, the answer is just 0, because y equals 0 is a solution to the differential equation. So that's our solution. Now the question is, on what interval does that exist? Well, it exists so long as the bottom is not 0. So what does that mean? Well, I need t squared to not equal 1 over a. Now what happens here? If a is negative, this is never true. So if a is negative, there are no points where they stop existing, so it exists for all t. However, if a is positive, we then have an issue at square root 1 over a. So the interval is from minus root 1 over a to positive root 1 over a. We have a very distinct case here, and the important thing to notice here is this equation is nonlinear, and the value of a matters in determining the interval of existence. For the first problem, which was linear, the value of a did not matter at all. It didn't affect at all what happened in the solution, it was just there no matter what. In this case, the value of a matters, and it matters quite a bit. We either get solutions that exist forever, or ones that exist in a very, very short time frame. Now the important final conclusion here is in every case here, our answer is an interval that contains 0. And that result is all that we have guaranteed from the nonlinear theorem for this problem. Because we started with y of 0 equaling a, the only we're guaranteed that the solution will exist and be unique on some interval containing 0. And whether we're in the case where it's negative and goes for all time, or it's positive and exists for a very short time, no matter what, we always get some interval containing 0. And so that's the tieback to the theorem here, is that no matter what you get, you're going to get some interval on 0. You can't guarantee more than that unless you don't remember the equation, right? If we hadn't been able to solve this all the way out, we would not get to the answers that are up here, right? We could not get to these until we actually solve the equation. So before you solve it, all you know, because they're continuous, you will get some interval around 0 for your solution. And that's an example that utilizes both the linear and the nonlinear version of this theorem for reasons and uniqueness, and shows how it connects to the actual intervals that we get for actual solutions that we can find.